Hello and welcome. So, today we will be looking at 2020 paper, and so what we are doing is we are solving linear algebra question from mathematics paper, right? So, we have already covered 2023, 22, 21, and today we will cover this 20. So, you will get the playlist for this, so you can go through that. And also we are solving questions according to whatever the syllabus of the data science and AI have. Okay, let's jump on to the question. So the first question is question number 9. Okay, so this is the question. Now question is given matrix M and ij is 1 2 3 4 and diagonal elements are all 0. So all the diagonal elements are 0. This is the one information that is given. Also another information is given that mij is equals to minus of mji. So if you know the element at 1 2, then you also know about the element at position 2 1, right? So that will be minus times of the minimum number of elements required to fully specify the matrix. So first of all, this m will be 4 by 4 because I varies from 1 to 4 and j, so it will be 4 by 4. And diagonal, all the diagonal elements are 0, it is given, right? So just put the diagonal elements 0. Now you will put all the elements according to this, right? So if you put here at first row and second column a, then here it will be minus a. So if you put here b, then here it will be minus b, and if you put here c, then here it will be minus c. It is nothing but the symmetric matrix. So okay, now if you put d here, so here it will be okay, so here it will be minus d, right? And if you put e here, then here it will be minus e, and if you put f here, then here it will be minus f. I hope I have made it correct. So we can check it. So if you see, this is the diagonal, right? And across the diagonal, if you look at across the diagonal, all the element will be, so this is correct. This one is correct, and this is across the diagonal, correct. So this c is correct, d is correct, e is correct. Okay, so how many elements do we need to specify this matrix? So we need 1 2 3 4 5 6. If we know these elements, then also we know these elements, right? So we need 6. So the correct answer for this is 6. Now let's move to another question, that is question number 12. So 9. Okay, so suppose that M is 5 by 5 matrix with real entries, and so what is this? So this is nothing but how we write the characteristic equation of matrix. So this is, and that character, what we have done is we have keep this as a polynomial. So here x is nothing but the eigenvalue, you can say. Then we have to check which one is correct. So the first option is that p of 0 is determinant of m. So we can simply put it here in this given equation. So p of 0, if we put at x is equals to 0, then here it will be determinant of 0 minus m. So it will be determinant of minus m, right? And this m is 5 by 5. So if we take the common minus 1, then it will be minus 1 to the power 5 determinant of m. So it will be minus of determinant m. So we can, so p of 0 is minus of determinant m. So this option is incorrect. Now next option is every eigenvalue of m is real if this relation is correct. So this one is the first eigenvalue, you can say this is another eigenvalue, and this is the third eigenvalue, right? Okay, so also if we can, so every eigenvalue m is real. So it is saying that every eigenvalue m is real. So but we do not have the information about every eigenvalue, right? So this is the one eigenvalue, this is second, and this is third eigenvalue, right? We are still left with two eigenvalues, and those two may be a complex or maybe a real, right? Okay, if we try to satisfy this given equation, so p1 of 0, so we have the polynomial, right, px. So what we can take such that p1 of plus p2 is equal to 0. So maybe we can take this kind of polynomial x minus 1. So if we then x minus 2 and x minus 3, and we will still left with two roots. So those two roots may be imaginary, so we can take x square plus 1. So this condition is getting satisfied, right? So p1, if you put p1 here, this whole equation will be 0, right? And p2 is also 0. So 0 plus 0 is equal to 0, and p2 plus p3, right, it will be again 0 and 0. So this one, whatever the relation is given, it is getting satisfied, but this can be, this root can be also imaginary or maybe real one, so we are not sure about that. So every eigenvalue of m is real, so we cannot say. So this option is also incorrect. Next option is m inverse is necessarily a polynomial in m of degree 4 if m is invertible. So if we take m inverse is necessarily a polynomial in m of degree 4. So we will have to see that m inverse is a polynomial having degree 4, and it is given that m inverse is invertible. So what we can do, we can maybe take a polynomial according to question. We have 5 by 5 matrix, So we can take a polynomial that is a0 plus a1x plus a2x square plus a3x cube plus a4 a5 plus a5x5. Right, now at the place of eigenvalue we can directly put the matrix M. So this matrix M, okay, so this px will be 0, right? Because what we do is we take the determinant of this. If we try to find the characteristic equation, then this will be 0 is equal to a0 plus a1 m plus a2 m square plus a3 m cube plus a4 m5, sorry, a4 plus a5 m to the power 5. Now if we multiply m, what we will do, we can simply put this my a to left hand side, so it will be minus a, right, a naught. Now let's multiply both sides m inverse, because m, according to option m, if n inverse exists, then we will have to check this, that m inverse is necessarily a polynomial in, so minus a naught. So obviously it will be a polynomial of, because if we multiply this side as m inverse, then it will be a5 m to the power 4 plus a4 m to the power cube plus a3 m square plus a2 m plus a1, right? So this m inverse is necessarily a polynomial in m of degree 4. So this option C is correct. Now let's look at option D. M is not invertible if m square minus 2m is equals to 0. So m square minus 2m is equal to 0, right? So from here what we can write as m minus m to I is equal to 0. So from here we can write m minus 2I is equal to 0. So m is equals to identity matrix, right? So if m is identity matrix, then we can invert, right? The inverse of identity matrix will be itself identity matrix. So this option is incorrect. M is not invertible, although by this relation what we are getting is m is 2 times of in identity matrix, and identity matrix are invertible. So this option is incorrect. So for question 12, option C is the correct answer. Now let's move to another question, that is 27. Okay, in 27, suppose B is a finite dimensional non-zero vector space over C, and transformation is given, and that T is transforming such that it maps to same space, is a linear transformation such that although we do not have this linear transformation in our syllabus, but we can look at this such that range of t. So this range of any matrix is nothing but the uh, column space, right? uh, so so transformation is happening such a way. So if we are applying this transformation t to any vector, then transformation is happening such a way that the uh, that it transformed to the same vector, or you can say the same space. Okay, so is a linear transformation such that range of t is equal to null space of t. Then which of the following statement is false? Okay, so in this case what is happening that range of t, that is column space. So if you have some matrix with uh, columns, then uh, then it's null space. So so if you, so this is your some matrix t, and this is your some matrix x. So if it is a null space, then what you will get is zero vector, right? Zero matrix. Or so, right? And according to question, this t, that whatever the column is here, that same column should be in null space also, right? So if you look at closely, that these two matrices are same, right? And let's take this a, then it will be also a, right? So a square is equal to this 0 matrix, right? So if you know the property about the nilpotent matrix, then you can easily go through the options, and you can pick the correct option for this question, right? So this this relation is this relation is saying that these two matrices are same, and since this matrix is a null space, so if this t is transforming this matrix, then what you are getting is the zero matrix, right? And according to this relation, these two matrices will be same. So a square is equal to 0. Now look at the statements. So the dimension of v is even, and what is this v? So this v is the complete dimension where these two uh, matrix belongs to, right? So so if we have given this relation, then according to option a, the dimension of v is even. It will be even. It is correct statement. How? Let me explain you. So these two matrices are same, right? So whatever the rank of this matrix, so whatever the dimension of this matrix will be, or whatever the columns will span this complete matrix, or whatever the column will span the complete column space, uh, it is the same set of vector that will span the columns of these matrix. So if if it has some two sets of basis vector, let's suppose two sets of basis vector that is spanning the complete column space, then it will also have the same two sets of basis vector that will span the column space of this matrix also, right? So if it has dimension x, then it will also have the dimension x, right? And this is one thing, right? Another thing is that, so this time so we will have to ultimate reach that what will be the dimension of v, and that dimension is even, right? So 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 this one is your column space, right? So if you have n number of columns, then then uh, the rank of null space will be n minus r, right? So let's suppose if it is has r, the dimension of this matrix is r, then uh, null space will also have the dimension r. So and if we add up these two dimensions, then it should be equal to the total dimension of the space, right? So it will be 2r, so it is multiple of 2, so that total dimension will be even, right? Again, now the next point, next option is 0 is the only eigenvalue of t. Okay, so if you look at this property that a square is equal to 0, so what matrix that will get multiplied itself and will give you a 0 matrix is the nilpotent matrix. So these matrix have the properties, uh, suppose if you, these matrix are generally square matrix, and if you have 2 by 2, then if you multiply to itself, then you will get the 0 matrix. And if this nilpotent matrix is 3 by 3, then for any value of k that is less than or equals to 3, you will get the 0. So maybe you will get the a square is equal to 0. If you are not getting a square is equal to 0, then you will get maybe a cube is equal to 0. So if any of these condition is getting satisfied, then you can say that this a is a nilpotent matrix, right? So also these nilpotent matrix have the property that the determinant of these matrix is 0. So let's take a 2 by 2 matrix, maybe if I can take it, maybe 2 1 and minus 4 and minus 2. So determinant of this is 0, correct? And if we multiply this by itself, so 2 1 minus 4 and minus 2, so it should be 0, right? So let's multiply it. So 2 times 2 4 and minus 4, that is 0. Again 2 times minus 4, that is minus 8 and plus 8, 0. 2 and minus 2, 0, minus 4 and plus 4, 0, right? So this matrix is nilpotent, right? And so the trace, what the second option is, the 0 is the only eigenvalue of t. So if you look at this nilpotent matrix, then it has the determinant 0. Also if you add up the trace, then it will be 0. So these are the properties of the nilpotent matrix, right? So lambda 1 plus lambda 2 is equal to 0, also lambda 1 into lambda 2 is equal to 0. So these condition will get satisfied only when both the eigenvalues are 0. So 0 is the only eigenvalue of t, so this is the correct answer, correct one. Also the first one is also correct, so we will have to find the false one, right? Now both 0 and 1 are eigenvalue of 2, so this is the false, incorrect. And t square is equal to 0, so this is the nilpotent matrix, and it has the property that if you multiply itself you will get the 0. So this is also correct. So according to question, option C is the right answer. Okay, so basically this question was based on the properties of nilpotent matrix, so you can look at that. Okay, now let's move to next question, that is 28. So we covered, okay, so 28 is here. Okay, so this one, let some matrix P, that is m by n, consider the following statements. So statement 1 is given that x p y is equal to 0 for all x belongs to 1 cross m. So x is so x p y, right, is equal to 0. So x is some row 1 and column m, so x will be this kind of matrix, right? And p is m cross n, so p will be this kind of matrix. So this is p, and m and y is n cross 1, so it has n rows and 1 column, so it will be this kind of. Okay, so if x p y, the product of these two, is equal to 0 for all x and y, then p is equal to 0. So for all x and y, that means if you are free to choose any x, any y, but you will still get the product 0, right? So for all x and y, this product will be 0 only when p will be 0, right? So statement 1 is correct. So you will have to read carefully this statement. So for all x and y, for all x and y, this should be true. This will be true only for all x and y only when this p will be 0. Otherwise, let's take x and y, and let's take any x and y, and you don't take p as equal to 0, then it will not guarantee that you will get the 0, right? So this statement is correct. Now statement 2, if p is equal to n, sorry, m is equal to n, so now we have the square matrix. If m is equal to n, p is symmetric, and p square is equal to 0, then p is equal to 0. Now again, what is, if you see p, right, so it is getting multiplied by itself, and what we are getting is 0, right? And also it is a square matrix, so we can take p, same example, right, this nilpotent one, because what we are doing is multiplying itself, right? Also there is one additional thing, is that p is symmetric. So can we say that a symmetric matrix is nilpotent? Is it possible that the symmetric matrix will nilpotent? So so let's suppose this P is symmetric matrix, right? So if you multiply two symmetric matrix, you will get the symmetric matrix. Why? What's the property of symmetric matrix is that suppose we have some matrix A that is symmetric, and if we take the transpose of this A, then what we will get is itself A, right? So if this P is symmetric matrix, and if we take this P square, then what we will get is a P transpose, and again it will be P into P. So what we will get is the same thing, right? P into P. So P is symmetric, and now can we satisfy this condition? If P is symmetric, then can we satisfy this condition? We can satisfy only when P will be 0, otherwise this condition will not get satisfied, that P square is equal to 0. So we have only one symmetric matrix, and at the same time that matrix is nilpotent, and that matrix is the 0 matrix, right? So both statements are true. So the correct answer for this 28 is A. Okay, now let's move to 28, 39. Okay, so this one, I think this Gauss Seidel method is not in the DS data science AI syllabus, but let's cover this question, but we will not cover this statement 2. What we will do, we will look at this statement 1 only, because it is based on the LU decomposition, and it is in the syllabus. Okay, so we have given this matrix M. Consider the following statement. Statement 1 is there exists a lower triangular matrix L such that M is equals to L into L transpose, right? So L is here the lower triangular matrix. So what we are doing is we are decomposing M to lower triangular and upper triangular, and here upper triangular is nothing but the transpose of this lower triangular. So we will have to check that for this matrix if this kind of relation holds or not. So how we can check is, first we can find the L lower triangular matrix, and we can take the transpose, then we can multiply if we are getting back this M, then statement 1 will be correct. Now if you look at the option, we have given this this alpha and beta value, right? So let's pick this option D. So I know that this option is already correct, so that is why I am picking. Otherwise you will have to go through all these options. Okay, so what we can do, so we can take alpha 5 and beta 3. So how this matrix will look like, so here it will be 5 and beta is 3, right? Now first of all, what we are going to do, we are going to decompose this matrix into L into U. So first of all we are going to apply the elimination, and we are going to get this upper triangular matrix. Now also we will have to trace the elimination matrix, and if we take the inverse of this elimination matrix, that matrix will be equal to lower triangular matrix. So to find this lower triangular matrix, we will have to trace the elimination matrix also, right? Okay, so let's first find this U. So what you will do, you will simply apply the elimination and make this element as 0. So you will keep the first row as it is, and you will take this one as a pivot. So I am also tracing the elimination matrix. So we have kept the first row as it is, and what we have done, what we will do to eliminate this 3, we will multiply by 3 by 5, right? Yes. So 3 by 5, 1, 0. Now what, here it will be 0, right? And here it will be 3 minus 3 into 5 by 3. It will be 5 by 3. It will be 5 by 3. So how much it will be? It will be 9 minus it will be 3 by 5. What I am doing? So what is the multiplier? Multiplier is 3 by 5, right? Yes. So elimination matrix will be, we have kept the row as it is, first row, and what we are doing is multiplying the first row by 3 by 5 and subtracting it from row 2. So it will be minus 3 by 5 here, 1, 0. So here it will be 0, and here it will be 3 minus 3 into 3 by 5. So 15 minus, here it will be 6 by 5, and here it will be 1 itself, and 0, 1, 0. So this is the first step of elimination. Now what we will do, we will take this as pivot and we will eliminate this. So what will be the elimination matrix? So here it will be 0, and here it will be, now multiplier will be 1 divided by 6 by 5, so it will be minus 5 by 6. And since we are okay, so here it will be 1. So this is the matrix E, and this will get converted into U. So 5, 3, 0, 0, 6 by 5, 1. Here it will be 0, here it will be 0, and what we have done is 2 minus 1 into 6, 5 by 6. So here we will get 12 minus 5, that is 7 by 6. So if you look, this matrix is upper triangular, right? This one is upper triangular. Now we have got this E, then how we can find lower triangular, that is L is equals to E inverse, and it will be 1 0 0 3 by 5 1 0 0 5 by 6 1, right? So this is our matrix U and this is our matrix L. Now according to statement 1, this lower triangular and this upper triangular should be uh, transpose of the lower triangular, but if you see that it is not looking like same, right? So what we can do, we can okay, what we can do, we can in lower triangular matrix, what you can do in row 1, if you see in upper triangular matrix we have this 5 3 0. So let's first take the transpose of lower triangular. The ultimate goal is to show you that this L transpose and this U is same, because what if we are getting these two same, then we have this M is equals to L into L transpose. So L transpose will be 1 3 by 5 and 0, and here it will be 0 1 5 by 6 0 0 1, right? Now you see that U and L transpose is not looking same. So what you can do, in row 1 you can multiply with 5, so it will be 5 3 0. In row 2 you can multiply with 6 by 5, so it will be 0 6 by 5, and here it will be 1, and in row 3 you can multiply by 7 by 6, so 0 0, so here it will be 7 by 6. Now if you see that this L transpose and this U is same, right? So this statement 1 is correct. So according to that, this statement is correct, this option is correct. So, and this Gauss-Seidel method is not in syllabus of DSAI, so I am not going to look at this. Okay, so now you will have one doubt. So if you have already studied how to decompose a matrix into lower triangular, upper triangular, then you can easily find this lower triangular and this upper triangular. So here I haven't explained you that how I am getting this elimination matrix and how I am getting this lower triangular matrix. That you can look into book. Also I have covered that in the matrix playlist, linear algebra playlist. You will find this this decomposition, LU decomposition. Alright, now let's move to this question number 41. So this question number 41, I cannot comment on this question number 41. I will have to look for the solution. So we will cover this in next lecture. And okay, I think that was all in linear algebra. So we will look this question number 41. That is remaining. Other questions we have already covered. So that is all in this lecture. Thank you.